In this video, I'm going to compare the definitions of kurtosis used by Excel and Mathematica, Wolfram Cloud, and R, the moments library. So let's start with Excel. They are giving me the definition right here that we are summing the difference between a data point and the mean, and dividing that by the standard deviation, and the kurtosis is related to the fourth moment. So then we are taking that to the fourth power and summing that up. Okay, so this quantity that's raised to the fourth power is the difference between a data point and the mean divided by the standard deviation. So that is basically a standard score or z-score. So that is a standard thing. Statistics take a data point, subtract the mean and divide by the standard deviation. And that one, if there were any units to the data, if we were measuring temperatures or heights or whatever, this would divide out and get rid of the dimensions. So we're working with something dimensionless. And then we're often comparing distributions to the normal distribution, and but a normal distribution is like a horizontal position on the x-axis, and we are sort of getting rid of that by subtracting of the mean, and it has a width, and we are getting rid of that by dividing by the standard deviation. So, and that's what we mean by standardized. We're turning any standard deviation into one that is sort of at the center with a standard deviation of 1. We're sort of making all normal distributions the same. We can do that to other distributions, but with the same idea, to sort of make them forget about any overall average, any overall spread, and then sort of start comparing just the shape of them beyond those two basic parameters. So that's why this thing has a name. It's a standard score or z-score, and that is part of this definition, of this, integral part of this definition. Okay, and then the second moment is about the spread itself, and the third moment was the skew, whether it was symmetric about the central point, and then the fourth moment is about how the data falls off. So the kurtosis is sort of somewhere in here is the black, I believe, is the normal distribution. It falls off has a certain big way of falling off from the central point. This sort of magenta or pink is a uniform distribution. It is very flat and then just drops off. This orangey one is probably some kind of power law Laplace distribution, and it is very peaked at the center, and so that's what this kurtosis is capturing, how you fall away from the center. Okay, so back to the definition. So that is this basic definition, and then we're adding them. So this is how you scale out for a score, but then we're doing something for all of the scores here. So then the number of data points sort of becomes a factor, and then we want to get rid of that. So for large n, this value out front, there are two n's in the numerator and 3 in the denominator. So for large n, we're effectively dividing by n. We are sort of scaling out the number of data points as well. So then our distribution doesn't depend on how many sample points we have within the distribution. It's more about just the shape itself again. Okay. Now I can't derive this formula for you in any way, but I do want to point out that one, this form here is going to be one of the things that differs between Excel and the definition used by other things. And then another point I want to make here is that this format here is designed to diverge if the number of points is 1, 2, or 3. So they're saying this is a fourth moment, and they want to say that you really need to have at least 4 points for it to make sense. So they devised a definition that that diverges, that says we have no knowledge of the kurtosis if we have fewer than 4 points. Okay. Another thing to point out is that people talk about kurtosis and excess kurtosis, and the definition. If you're making that distinction, then what you have in Excel is an excess kurtosis. And again, we often compare things to a normal distribution. And so the kurtosis of a normal distribution is 3, whereas the excess kurtosis of a normal distribution is 0. And so we see that here, that again, for large n, if this is n squared in the numerator for large n, and n squared in the denominator for large, so we're subtracting 3. So that is subtracting off the kurtosis of a normal distribution, making this an excess kurtosis definition. Okay, so that's so now let's just convince ourselves that Excel's not lying, that is indeed it. So I had some data. I did the data point minus the mean divided by the standard deviation, the sample standard deviation. Again, Excel offers you a sample deviation and a population deviation. They're using the sample deviation and raising that to the 4th power. And so that's what I have here. I have all the individual elements. And then here I am from the definition in Excel. I am summing them all up. I have 100 points here, but what I did, just to keep it generic, was I counted up the data points, and that's in E6. So then I am doing all of this n plus 1, n minus 1, n minus 2, n minus 3 stuff here with E6, because that's my number of points. And I did duplicate up here, which was just Kurt. So this is indeed their definition. It is not what we're going to see in, say, R or Mathematica. It is still based on the sum, but they're going to be multiplying by n and dividing by n minus 1 squared. So their definition is not going to diverge for 2 or 3 data points like this one will. So the Excel definition has this idea built into it that if we don't have 4 points, we're going to claim we have no knowledge of the kurtosis. The Mathematica and R definitions are not building that in. Okay, so let me show you. Here's R. Just again, this is the same set of data. And I ran the kurtosis, and here's my kurtosis 2.8 2.8415, etc., 2.8415. So this agrees with this calculation of that sum of fourth moments of z-scores to the raised to the fourth, and then multiplied by the number of points and divided by the n minus 1 squared number of points. Okay, so that is what, oops, sorry. So that is the definition that this moments library is using in R, and it is also what is being used in Wolfram. So again, here's the same data. I called it my data here. That's the same data I had in Excel, and that's the skewness. I was doing that in a previous thing, but here is the kurtosis. So I'm taking the kurtosis of my data to sort of 7 significant digits and figuring out numerically, because Mathematica likes to do things exactly, and I'm getting, again, 2.8415. So that is the definition used by Mathematica, and because Mathematica also works symbolically, we can also just put in a set of data, a symbolic set of data. So I just said 6 points A, B, C, D, E, F, and evaluate the kurtosis. And we see here is that sort of z-score for each of the things raised to the fourth. Here is the n out here, 6. There were 6 data points. And then this is not quite down here, the standard deviation, because the standard deviation you would take divide by n minus 1, and so then there were 4 of them. So you divide by n minus 1 and then take the square root, and then there were 4 of them. So that's the n minus 1 squared that that we saw over here in this definition. The n minus 1 squared is once you turn what's their denominator in this Mathematica expression into the standard deviation of the z-score, then that pops out the n minus 1s. Okay, so there's a difference in definition, 2 differences in the definition between Excel and R and Mathematica. One is that Excel's definition is an excess kurtosis, so the normal distribution will give us 0 as opposed to 3. And R and Mathematica are also not doing this sort of n minus 2, n minus 3 stuff to say that forcing the expression to diverge when we have fewer than 4 points. Okay. And then I just did one more thing here. I used random variate and normal distribution. And this was just a normal distribution is defined by its mean and standard deviation. So I just picked 86 and 6, and I generated 1,000 points that had that behavior. And from a normal distribution, I just want to calculate the kurtosis of this and see that for a normal distribution, it's supposed to be about 3. So I just used Mathematica to generate some normally distributed data. I chose 1,000. Now I'm having picture problems. All right. So let me rerun this so that it will clean up the image. So I'm generating 1,000 data points, 1,000 samples, and then I'm going to take the kurtosis of it. And you see my previous kurtosis was around 3. This is going to be a different number, but also around 3. Okay, so I'm hovering around 3, and then I'm going to do the uniform. I'm having the same issue here. I'm doing a uniform distribution, and this is the sort of min and the max. So that's how uniform distribution works between a min and a max. And again, shift enter, and I'm generating 1,000 points from a uniform distribution. And then down here, I'm going to grab its kurtosis, and it was 1.76 here. And if I look back here in this comparison of kurtosis, these values here in this graph are excess kurtosis, and so the normal distribution was 0, and the uniform distribution was minus 1.2. So if I were to subtract 3, I would be in the vicinity of, like, this is, you know, if I round up 1.8, and if I subtract 3 minus 1.2. So we are sort of seeing this, a uniform distribution, as if you're doing excess kurtosis, a negative value. The normal was 0, and then things that are sharply peaked have a higher kurtosis. Okay, so that's what I wanted to show you, these different definitions used by these different packages. Thanks for your attention.